Dear students, in this video, we are going to discuss some topics of Module 5 of Applied Linear Algebra. The topics we have to discuss in this module are eigenvalues, eigenvectors, properties of eigenvalues and eigenvectors, diagonalization, orthogonal diagonalization, minimal polynomial, and Jordan canonical form. Of these topics, eigenvalues, eigenvectors, and properties of eigenvalues and eigenvectors are discussed in this video. If A is an nth order square matrix and X is a column vector of n unknowns, consider the equation Ax equals lambda x, where lambda being a constant. The values of lambda that satisfies this vector equation are called the eigenvalues of A, and the vector x satisfying this equation is called the eigenvector corresponding to lambda. Eigenvalues can be any constant. It can be real or imaginary. They can be distinct or repeated. The collection of all eigenvalues is called the spectrum of A. The largest of the absolute values of the eigenvalues is called the spectral radius. Now we will discuss how to find out the eigenvalues and eigenvectors. In the last slide, we have seen that the eigenvalues are the values of lambda that satisfies the equation Ax equals lambda x. This equation can be written as Ax minus lambda Ix equals 0. As the RHS and LHS are of different orders, in order to combine them, we have to make them of same order. For that, multiply the RHS by the identity matrix of order n and then subtract RHS from LHS. Thus, we get Ax minus lambda Ix equals 0, or A minus lambda I into x equals 0. In the earlier module, we have come across system of linear equations. Matrix A minus lambda I into x equals 0 is a homogeneous system of linear equations, and this system has a non-trivial solution only if determinant A minus lambda I equals 0. Determinant A minus lambda I equals 0 is called the characteristic equation of A, and this will be an nth degree equation in lambda. Eigenvalues are the roots of this equation. For each lambda, we can solve the system A minus lambda I into x equals 0, and the solutions are the eigenvectors corresponding to these eigenvalues. Now we will try to do some problems. First problem, find the eigenvalues and eigenvectors of A equals first row 3, 5, second row 1, minus 1. To find the eigenvalues, first we have to write the characteristic equation, which is determinant A minus lambda I equals 0. To find A minus lambda I, we just need to subtract lambda from the main diagonal elements. Thus, determinant A minus lambda I equals 0 implies determinant 3 minus lambda, 5, 1, minus 1 minus lambda equals 0. Evaluating the determinant and equate to 0, we get lambda square minus 2 lambda minus 8 equals 0, whose roots are minus 2 and 4. Thus, the eigenvalues of the given matrix are minus 2 and 4. To find the eigenvectors, we need x. Since the order of the given matrix A is 2, choose x as a column vector of 2 unknowns. Let it be column vector x, y. A minus lambda I into x equals 0 implies matrix 3 minus lambda, 5, 1, minus 1 minus lambda into column xy equals 0. When lambda equals minus 2, this system becomes matrix 5, 5, 1, 1 into column xy equals 0. Reduce the coefficient matrix into its echelon form and substitute back in this. We get 1, 1, 0, 0 into xy equals 0. Converting this into equations, we get x plus y equals 0. Now, the rank of the coefficient matrix is 1, which is the number of non-zero rows in the echelon form, and the number of variables is 2. The variables are x and y. Giving arbitrary value to n minus r equals 1 unknown and choosing it as y equals a, the solution is x equals minus a, which is equivalent to minus 1, 1. Any constant multiple of this vector is an eigenvector corresponding to lambda equals minus 2. When lambda equals 4, the system a minus lambda I into x equals 0 becomes minus 1, 5, 1 minus 5 into xy equals 0. The coefficient matrix can be reduced into its echelon form, and when we substitute back into this system, it becomes minus 1, 5, 0, 0 into column xy equals 0 implies minus x plus 5y equals 0. The rank of the coefficient matrix is 1 and the number of variables is 2. Again, n minus r equals 1 and giving arbitrary value to one unknown and choosing it as y equals a, the solution becomes x equals 5a, which is equivalent to 5, 1. Any constant multiple of this vector is an eigenvector corresponding to lambda equals 4. So the eigenvector corresponding to lambda equals 4 is 5, 1. Now we will try to find out the eigenvalues and eigenvectors of another matrix. It's a 3 by 3 matrix. Minus 2, 2, minus 3, 2, 1, minus 6, minus 1, minus 2, 0. As in the previous question, the characteristic equation is determinant A minus lambda I equals 0 implies determinant minus 2 minus lambda 2 minus 3 2 1 minus lambda minus 6 minus 1 minus 2 minus lambda equals 0. Instead of finding out the value of the determinant in the direct way, we can find it out in a simpler way. This is applicable only for 3 by 3 matrices. Since the order of the matrix is 3, the characteristic equation will be of degree 3. So, the first term will be lambda cube. The coefficient of lambda square will be minus trace of A. Trace of A means the sum of the diagonal elements. Coefficient of lambda will be the sum of the cofactors of the diagonal elements of A, and the constant term will be minus determinant A. Finding out these and substituting in this, we get the characteristic equation as lambda cube plus lambda square minus 21 lambda minus 45 equals 0, whose roots are 5, minus 3, minus 3. Hence the eigenvalues are 5, minus 3, minus 3. Here minus 3 is a repeated eigenvalue. To find the eigenvectors, we need to choose capital X. Since the order of the given matrix is 3, choose X as a column matrix of 3 variables. Let it be column vector X, Y, Z. The system A minus lambda I into X equals 0 becomes matrix minus 2 minus lambda, 2 minus 3, 2, 1 minus lambda, minus 6, minus 1 minus 2 minus lambda into column vector x, y, z equals 0. When lambda equals 5, this system becomes minus 7, 2, minus 3, 2, minus 4, minus 6, minus 1, minus 2, minus 5 into column x, y, z equals 0. As in the previous case, Reduce the coefficient matrix into its echelon form and substitute back. We get 1, 2, 5, 0, 1, 2, 0, 0, 0 into column x, y, z equals 0. Here, the rank of the coefficient matrix is 2 as there are 2 non-zero rows in the echelon form and the number of variables is 3, namely x, y and z. N minus r equals 3 minus 2, which is 1. So choosing one arbitrary value or giving arbitrary value to one variable, the solution is x equals minus a minus 2a a, choosing z equals a. Hence the eigenvector corresponding to lambda equals 5 is minus 1, minus 2, 1. Any constant multiple of this vector is again an eigenvector corresponding to lambda equals 5. Now, for the next eigenvalue lambda equals minus 3, the system A minus lambda I into x equals 0 becomes 1, 2, minus 3, 2, 4, minus x, minus 1, minus 2, 3 into column x, y, z equals 0. As in the previous case, reducing the coefficient matrix into its echelon form and substituting back, we get 1, 2, minus 3, 0, 0, 0, 0, 0, 0 into column x, y, z equals 0. Here, the rank of the coefficient matrix is 1 and the number of variables is 3. So, n minus r equals 2. Giving arbitrary values to two unknowns and choosing them as y equals a and z equals b, the solution is x equals minus 2a plus 3b a b. We can write this vector as the sum of two column vectors as follows. Minus 2a plus 3b, a plus 0b, 0a plus b, which is equivalent to column vector minus 2a, a, 0a plus column vector 3b, 0b, b. Hence, there are two eigenvectors corresponding to the eigenvalue lambda equals minus 3 and they are minus 2, 1, 0 and 3, 0, 1. Now, we will look into some properties of eigenvalues and eigenvectors. First one, the sum of the eigenvalues of the matrix A is same as the trace of A. That is, the sum of the entries on the main diagonal of A. The product of the eigenvalues is same as the determinant of the matrix A. For a triangular matrix, the eigenvalues are the entries on the main diagonal. In a triangular matrix, all the elements below the main diagonal or above the main diagonal will be zeros. In that case, the eigenvalues are the entries on the main diagonal itself. The eigenvalues and eigenvectors of A transpose are same as that of A. If we know the eigenvalues of the given matrix A, from that we can find out the eigenvalues of Ka, A inverse, A to the power of m and A plus Ki. If lambda 1, lambda 2, etc. lambda n are the eigenvalues of A, then to find out the eigenvalues of K into A, just multiply the eigenvalues of A by that constant K. To find out the eigenvalues of A inverse, just take the reciprocals of the eigenvalues of A. To find the eigenvalues of A to the power of m, lift the eigenvalues of A to the power m. And to find out the eigenvalues of A plus K times an identity matrix, just add K to the eigenvalues of A. In all these cases, the eigenvectors will be the same as that of A. Now we will try to prove these properties. First four properties are trivial, so we will start with the fifth one. If lambda 1, lambda 2, etc. lambda n are the eigenvalues of A, then k lambda 1, k lambda 2, etc. k lambda n are the eigenvalues of Ka, and the eigenvectors of Ka are the same as that of A. Let us assume that lambda is an eigenvalue of the matrix A. Lambda is an eigenvalue implies it should satisfy the equation Ax equals lambda x. Multiplying both sides by the constant k, Kax equals k lambda x implies k lambda satisfies the equation Kax equals k lambda x, or k lambda is an eigenvalue of Ka with the same eigenvector x. Property 6. If lambda 1, lambda 2, etc. lambda n are the eigenvalues of A, then their reciprocals are the eigenvalues of A inverse, and the eigenvectors of A inverse are the same as that of A. Let us begin with the assumption that lambda be an eigenvalue of A inverse. So we have to prove that 1 by lambda is an eigenvalue of A. Since lambda is an eigenvalue of A inverse, it should satisfy the equation A inverse x equals lambda x. Multiply both sides by A. A inverse x equals A lambda x. We know that A into its inverse equals I, and I into any matrix is again that matrix itself. So x equals lambda Ax, or Ax equals 1 by lambda x, implies 1 by lambda satisfies the equation Ax equals 1 by lambda x, or 1 by lambda is an eigenvalue of A with the same eigenvector x. Property 7. If lambda 1, lambda 2, etc. lambda n are the eigenvalues of A, then lambda 1 raised to m, lambda 2 raised to m, etc. lambda n raised to m are the eigenvalues of A raised to m, and the eigenvectors of A raised to m are the same as that of A. We are going to prove this by the method of mathematical induction. For that, we need to prove the result first for m equals 2, and assuming that the result is true for m minus 1, we have to prove that it is true for m. First, we will prove that the result is true for m equals 2. Let us assume that lambda is an eigenvalue of A. Since lambda is an eigenvalue of A, it should satisfy the equation Ax equals lambda x. Multiplying both sides by A, we get A square x equals lambda into Ax. Since Ax equals lambda x, we can replace Ax by lambda x, and we get A square x equals lambda square x. Implies lambda square is an eigenvalue of A square with the same eigenvector x. Hence the result is true for m equals 2. Now assume that the result is true for m minus 1. That is, we assume that lambda raised to m minus 1 is an eigenvalue of A raised to m minus 1 with the same eigenvector. That means lambda raised to m minus 1 satisfies the equation A raised to m minus 1 into x equals lambda raised to m minus 1 into x. Multiplying both sides by A, we get A raised to m into x equals lambda raised to m minus 1 into Ax. Again, since lambda is an eigenvalue of A, we have Ax equals lambda x, and we can replace Ax by lambda x. So we get A raised to m x equals lambda raised to m minus 1 into lambda x, or A raised to m into x equals lambda raised to m into x. That means lambda raised to m is an eigenvalue of A raised to m with the same eigenvector x. Hence, by mathematical induction, the result is true for all values of m. Property 8. If lambda 1, lambda 2, etc. lambda n are the eigenvalues of A, then lambda 1 plus k, lambda 2 plus k, etc. lambda n plus k are the eigenvalues of A plus ki, and the eigenvectors of A plus ki are the same as that of A. Here also we start with the assumption that lambda is an eigenvalue of A, means it should satisfy the equation Ax equals lambda x. Adding kx to both sides, we get Ax plus kix equals lambda x plus kx. Implies A plus ki into x equals lambda plus k into x, which shows that lambda plus k is an eigenvalue of A plus ki with the same eigenvector x. So, we can compute the eigenvalues and eigenvectors of such matrices with the help of these properties. Sample problem. Compute the eigenvalues and eigenvectors of A and A raised to 4 if A equals 0 to 2, 3. Here we have to find out the eigenvalues and eigenvectors of A. To find out the eigenvalues of A raised to 4, take the fourth power of eigenvalues of A, and the eigenvectors of both these matrices will be the same. In the same way, in the second question, to find the eigenvalues of A inverse, find the eigenvalues of A and take the reciprocals. The eigenvectors will be the same for both the matrices. Thank you.